slight delay. Where's the view screen? So the slides today are new. So we'll added a additional sort of section to this class on supervised approaches and how that sort of extends from the things that we started last week with advanced segmentation, and so how you move beyond some of the older computer vision techniques we've discussed to some of the more machine learning supervised approaches. So in terms of reading material, this of course looks very different than some of the things we've done before. So there's of course whole courses dedicated to this, or dedicated to each little section of what we're going to talk about today. If you really want to know more, I would recommend looking into those courses. There's also a plethora of online courses which offer similar sorts of material. There's quite a few interesting books you can read about this. Decision Computer Analysis, Advanced Recognition in Medicine is, I think, the title of the book. If you click on the link, you end up there. Sorry, the title came in incorrectly. But it's a book about decision forests in computer vision and medical image analysis. It's from the group at Microsoft that came up with the Connect, as I mentioned last time. Then sort of UNet convolutional networks for biomedical image segmentation, which we won't get into specifically in this lecture, but that will be sort of the jumping point. So we'll go from this as really the baseline material to UNet as sort of the next steps to get beyond that. So in terms of what we're going to cover today, there's sort of the methods that we'll go over briefly, this idea of pipelines, then classification, regression, and segmentation, and then we'll go to sort of the old lecture. So in terms of the basic methods, we're going to cover a number of fairly simple approaches here. We won't really talk much. Have people covered classification and regression? Have you heard of that before? Or who has never heard of it before? Easier. And who's heard of it before? And who's used it? Okay, so 2 or 3. Okay, so I guess I'll cover it. If you have questions, of course, feel free to ask. This is not an in-depth analysis. This is just really the very basics. But basically, we have a few methods that we use, and we sort of don't get into the whole area called support vector machines, because that's sort of too specific and too detailed for what we're doing now. But we'll cover sort of decision trees, linear regression, random forests very briefly, and talk about how we can apply them to the problems we're working with. So the sort of main thing to understand with these supervised models is that you have this idea of a training phase and a predicting phase. And so in the training phase, this is where you have a model that has some parameters that you're trying to fit. You put data in where you know what the result should be, and you tweak the parameters so they better match the outputs that you expect. So, you know, with linear regression, this is curve fitting, you know, fitting a linear line and trying to figure out what the slope and the offset are so that you get good results. Predicting is then sort of the next step in this process, where once you've built a model, you sort of freeze all of the parameters inside it, and then you can apply the model to new data sets. And so generally, if you think back to sort of a linear regression or a linear curve fitting, if you have new data or one new data point, it's very difficult for you to decide how you would update the slope or the intercept based on one new data point. So you can say that the one new data point maybe doesn't get fit by the curve very well, but it's unclear how you would use one point to make a better fit. You could add it to your original data and then do the fit from the beginning, but in generally it's very tricky once you have a finished model to update it. One of the sort of notable exceptions to this is this whole area of neural networks, where you can continuously train models and start and stop and update them with single points, and they have better ways of dealing with this. So in terms of some practice data that we'll look at. Scikit-learn, which is a package we use quite a bit in this class, has a function called make blobs, which sort of makes these different blobs of data on the XY axis, where if we zoom in here, we see we end up with, I think, 100 points divided up into 3 groups. And so it gives us the positions of each point and the groups. And so what this helps us do is sort of have practice test data for seeing what these methods do. And so this is what we'll apply the different techniques we have to. So nearest neighbors is as simple as it sounds. It's an incredibly basic technique where basically if you have a point, it says what's the nearest point to what you have put in. So it memorizes your inputs and spits out the outputs that it expects to get with that. And so this is sort of the fundamental basic approach. I don't think anyone would call this computer intelligence. And this is the starting point for a lot of the things that you'll do. And so nearest neighbor just finds the one nearest neighbor, k nearest neighbors, then finds the k, whatever k is, nearest neighbors, and averages them together. And so if you're looking to get sort of more stable results, you might not just use one, but you can just use one and simply memorize your data. And so for a very basic example of this, we can make one of these classifiers very simply, where we say our input is this x, which is 0, 1, 2, 3, and our output is this y, I am a dog. And so we have clearly no linear relationship or anything between the input and the output, but we're able to build a model that does this one neighbor classifier on this data set. And so basically it says 0 maps to sort of I, 1 maps to am, 2 maps to 3 maps to dog. And so if we were to just test this on that input, it might look like we have an algorithm that can actually sort of speak English. It's able to come up with a sentence. It was able to take the 0, 1, 2, 3 and make a sentence, I am a dog. But it in fact has no idea what any of these things mean. It simply memorized the inputs. And so this is, I think, a very useful technique for appreciating what networks are capable of, or what machine learning methods are capable of doing. So that they don't have any understanding for what the letters are, what words are, what grammar means, but it's still able to make an incredibly reasonable sentence because it was trained with very reasonable sentences. And of course, if you start to take things that are off the immediate axis, if you take a point like 1.5, it will say am, because that's the second word, so it rounds 1.5 to 2 and says that's the closest one and spits it out. And if you take a point at 100, even though our axis only went to 3, it will say dog, because the nearest point to 100 is 3. And so you have now a completely continuous way of representing this data, but it doesn't do anything intelligent. There's no extrapolation. It doesn't try to figure out, after dog there might be a period. It has no understanding of any of these things. It simply has mapped sort of our inputs to our outputs. So now for kind of a more practical example, we can go back to sort of the simulated data set where we have these 3 different groups. We can now fit a nearest neighbor classifier to this data set. You can ignore all of these parameters. These are more how this is in fact implemented to do it efficiently. Because of course, if you have billions of points, it can be difficult to go through all your points to find out which one's closest. And then we sort of can train our model and apply it to a new set of data. And so what we have here is we have the training data there. Apparently a typo as well. And we have a grid of testing points. And so basically we generate, you can look at the code above if you're interested, points for every possible XY coordinate in sort of this range. And so we end up with this grid, and we predict for each point which group it should belong into. And so what we see, and this is sort of an important idea, is this idea of sort of a decision surface. And so that we have our initial training data, and we can apply it over the whole axis and see this is sort of where it's differentiating between group 0, group 1, and group 2. Group 0, 1, 2. And where those boundaries are based on the points that it has inside of it. And so this gives us a little bit more insight into what the model's actually doing and what it has decided is sort of an important criteria for making decisions between groups on. Linear regression, so to switch to a slightly different method, is this idea of sort of fitting a linear curve to a model. And so rather than finding the nearest point and trying to classify it, you try to fit a linear curve to sort of the different variables you have. It's a very important method to understand because it's simple. So it obviously doesn't deal with complicated problems. Using linear regression to try to identify pictures of cats would be very difficult to do. But it's easy to understand, interpret, and fast to compute. And so these sort of have a massive value that when you're dealing with a really complicated problem, you want to be able to understand what your model's doing. And if you're dealing with things, particularly in sort of a medical or a manufacturing environment, you want to be able to predict sort of what's the worst case scenario. So if you end up with a value going in that's 100 times higher, how much higher is your output? Is it going to be 100 times? Is it going to be 1,000,000 times? Is it going to be 0.1 times? And so with linear models, this is obviously fairly straightforward to do. You have these properties you can examine. You can look at what variables are going in, and you can do sensitivity analyses there. With some of the other models and more complicated approaches, you could end up having a small, 1% change in your image that has a 1,000% impact down the line on whatever you're doing. So again, we can do this sort of very, very simple example where we put in a bunch of points. So we have the x points as 0, 1, 2, 3. And now instead of words, we sort of have 10, 20, 30, 40. And so it fits lines to this, and we can also see what it does. By going to slope and L-reg intercept. Oh, this doesn't have that. Intercept coefficient. Yeah, so that what we see is, it took this data, it fit it, and what it decided was that the slope or the coefficient, because there can be multiple dimensions in what you're doing, was 10, which makes sense because 0 goes to 10 and 1 goes to 20, then that slope is very easily identifiable as 10, and that the intercept is 10. And so the offset between 0, the y-axis is, x-axis is 10. And so it did what we expected it to do in a very simple situation, which is good. We want to start off with the most simple possible data set before we get into things more complicated. We can see what happens if, we try to predict minus 100 or predict 500. It extrapolates, so it takes this linear slope and it goes, to minus 990 if you go to minus 100, or plus 5,010 if you go to 500. And so it sort of assumes this trend is followed in a linear fashion, even for points that are wildly outside of sort of the domain that we've trained the model on. And so that's an important sort of distinction between this k-nearest neighbors, where k-nearest neighbors will never give you anything that wasn't in your input. It's sort of restricted by the domain of your input, while this model is able to produce things that it has never seen or was never trained on before. And so now we can apply this to a very similar data set. So we change the parameters. So we have two groups now. So this is sort of group 0 and this is group 1. We can fit this linear model to the data. We can do the same sort of analysis we did before. So we now end up with two slopes. So we end up with a slope in x and a slope in y. Because what we've done is we've said basically there's this third parameter, which is this group, which is 0 to 1. So this x is here. And we want to fit sort of a line through it where we take into account the x position and the y position to try to predict that. And so it's fundamentally not any more complicated than what we've done before. It's just adding a new variable to what we're looking at, and it makes it a little bit more difficult to visualize because now this isn't really a 2D plot, it's sort of a 3D plot that we're looking into. But fundamentally, all of the math and all of the things behind it remain the same. And so now we can apply this to the whole data set, where we do this sort of test pattern like before, where we have sort of the training data set. We then create points everywhere in this graph and can show that our model has sort of learned this linear trend in the data. And so clearly for a point like this, it gets it incorrect. This should be blue, and here we see that this is green. But it gets the general trend quite well. And so it has sort of given us an ability to take any point on this xy axis and say which sort of value that point should have. You can also restructure that as sort of an image itself, where you can then show the whole image for what's going on. So for trees, this is sort of the last one we'll cover in detail right now. You can use decision trees to do very similar sorts of things, where you have inputs and outputs. In this case, we'll focus on classification, where you give it an x vector. So here 0, 1, 2, 3 is the data we give it in. And the output is sort of 0, 1, 0, 1. So we have two groups, one is 0, one is 1. And what decision trees do is when you give it that data, it goes through and breaks up your x input into different groups. So it applies rules in sort of an iterative fashion to split the data into different groups based on the outcome that you're looking for. And so what we see is that if you take sort of the x0, so there is only one x variable, if it's less than 0.5, it goes in this true category. If it's greater than 0.5, it goes into this category. And then we see if it's less than 1.5, it goes this way. If it's greater than 1.5, it goes this way. If it's less than 2.5, it goes this way. If it's greater than 2.5, it goes this way. And so basically what this has done is this has taken our 0, 1, 2, 3, and it's transformed it into a list of rules that we can look at and apply to the data. And so that's really the thing that makes decision trees so useful, is that it's able to learn fairly complicated true or false rules. And it does this from the data itself, and it's very easy to visualize. So that you end up with a model where you can, with this nice little package, show exactly what the steps it's going through are in order to make a decision that you've given it. So we can, again, apply this data set we have before with 3 groups. We can learn a tree to classify, or train a tree to classify these different groups. And we end up with fairly simple rules. So it looks at the y-coordinate, is it greater than or less than 6? And then it looks at the y-coordinate again, is it greater or less than negative 1.3? And that's sort of the criteria it uses. And that we see, it comes up with, when you do this sort of grid of points and apply that set of rules to all of them, it comes up with a classification like this. And so X information clearly is useful. It decided not to use it because it wasn't as easy as using just the Y coordinate. And so it's come up with a fairly simple representation for the data that may or may not be applicable for what we're doing, but it's very easy to understand why it decided this was in group 1 and not group 0. And so with these methods, it's important to kind of appreciate how they work and know how to apply them, because there's a lot of different problems you can solve using these kinds of approaches. And they are quite easy to set up, particularly in tools like KNIME or Python, where you have all of these packages which have been pre-made that make it as simple as possible to sort of combine these different approaches together and apply them to data sets. So we'll skip random forest for now. Are there any questions on those basic techniques? Yeah.
When did you use which one?
So it depends a bit on the kind of problem you have and how you sort of expect the relation between the input and the output to be. And so I think for most things, you can apply sort of the k nearest neighbors as a starting point, as sort of your baseline to figure out how well do you do by simply guessing what the nearest thing is. You know, it's kind of like if you're trying to predict the weather, the easiest thing for predicting the weather is to say the weather tomorrow will be the same as today. It doesn't require any understanding of physics or meteorology. It's just saying that. And so this gives you, I think, a very good baseline that works well for a lot of systems. You know, linear regression would make sense if you somehow expected there to be linear relationships in what you were doing. And then sort of decision trees and these more complicated approaches when you expect there to be more intricate relationships between them. So that, you know, if you have sort of little groups that form together, decision trees can extract those fairly reliably, where other techniques might not do as well. But there's not really a blanket tool that solves every problem perfectly. It requires quite a bit of practice. But I think one of the important things is that when you make more complicated models and more complicated approaches, you want to be confident that your more complicated approach is better than simply a k nearest neighbor. And when you read a lot of the papers that come out today in this area, they haven't done that comparison. They say we've built this model that can identify cancer, you know, with 90% accuracy, and you can say, well, if you just say the person's healthy, because most people don't have cancer, that's 99.9% accuracy. And so your model with 90% accuracy is actually much worse than no model at all. And so this is sort of the point that you want to be improving upon very simple guesses, not building from scratch in that sense. So one of the important things with this, which sort of relates back to one of the things we mentioned earlier in this course with sort of reproducibility and combining lots of different steps together, is this idea of pipelines. So we have more of this at the end, but this is just sort of a brief intro, because a lot of these tools, as you saw before, you know, were not taking images as input. They were taking tables of X, Y coordinates. You know, they're very good at classifying flowers based on how long the petals are, but they don't really deal with images well. And so this is why we have this pipelines part, because this lets you incorporate some of the image processing tasks into what you're doing and incorporate a large number of different steps together in order to perform a more complicated classification or other problem. And so if we start off with sort of this you know, very simple data set like we had before. We have all of this code because this hasn't been integrated yet into scikit-learn or scikit-image. People are working on this, but they haven't decided on a final way of doing it. And so for now, you'll need these extra steps in order for everything to work, but you don't have to concern yourself with the details unless you're interested in looking at that in more detail. And so basically what we can do here is we can take these points and we can apply some of the